So hello everybody, we are back to our plasma class again, and we'll be starting in this class something different from electromagnetic waves, that is electrostatic waves in plasma. I'll tell you what is electrostatic waves and how will it behave once it is excited in plasma. So in the last class what we have done, we were getting the plasma kinetic equation and then Blasov equation, and we got that if we neglect the collisional contribution, then that plasma kinetic equation reduces to Blasov equation, and possible solution of Blasov equation we tried to understand from the fact that total derivative of the Blasov equation is giving 0. So from that this distribution function must be some constants of motion in such cases, and depending on the kind of situation, whether electric field is there, magnetic field is there or they are not. So we found that there are certain kind of solution possible for this Blasov equation. We can guess them. So starting from there, we are now trying to understand whether the plasma can support electrostatic waves propagation. So first of all, what is electrostatic waves? So we'll be applying this plasma kinetic equation to understand behavior of such waves. Now electrostatic waves are those which has no magnetic field, and wave propagation is in the direction of the electric field. You know that electromagnetic waves, which all of us are familiar with, it has two components, electric and magnetic field, which are perpendicular to each other, and they propagate in a direction which is perpendicular to both electric and magnetic field. So this we all know. Now to understand that electrostatic waves will have only electric field and no magnetic field, how can we prove that thing? So let us assume that the electromagnetic wave is propagating in the x direction. So as you can see here, we have taken one expression for electric field as E0x e to the power minus I omega t minus kx into I. So this is I is the unit vector, so it is propagating in the x direction. Now if possible, let us assume that a general magnetic field also possible for such case of electrostatic waves, and that may have all the components in x, y and g direction as we have written here. Now Maxwell's equation is true in all the cases. So if we take curl of this E, because E is unidirectional, so you can just take it simply from expression for curl. So it comes, it has I cross I is 0, so it will have only j and k components, and you can see that when you take proper sign, it comes minus ik E0y exponential of minus I omega t minus kx in j, and ik E0z e to the power minus I omega t minus kx in k. So this is, you can write it as something minus ik and then I cross E. Okay. Now I is the direction of the propagation vector, and E is also in the direction of I. So I cross E, this is definitely going to give you 0. So what we are getting, that curl E is equal to 0. Now from the Maxwell's equation, we know that here what we are getting, that curl E equal to minus del B del T, and del B del T for this expression you are getting that it is just I omega into B itself. Okay. So if that is the case, then you know that curl equal to minus del B del T, and minus del B del T is just this I omega B, and if you equate this to this curl E, that is giving you 0, and del B del T is giving you I omega B, so I omega B equal to 0, so that gives you B equal to 0. So this is a very simple way to prove that electrostatic waves cannot associate any magnetic field. So this is the very special nature of this kind of waves in plasma, where the magnetic field is 0, and it is only electric field which propagates, and the direction of propagation and the direction of the electric field, they are the same. So with this we start understanding the propagation of electromagnetic waves in plasma. In our early classes we have already learned that for electromagnetic waves plasma acts as a refracting media, and the refractive index also we have calculated, that appeared in terms of this plasma oscillation frequency, and we studied when it will propagate, when it will not propagate. All these things we studied in those classes for the propagation of electromagnetic waves. Now here we are trying to do similar kind of thing for electrostatic waves, which associates no magnetic field and the electric field is in the direction of propagation. So the propositions are I have just listed over here. So they are what I am telling, this direction is same as the direction of propagation of electric wave, electrostatic wave. And then electrostatic wave doesn't associate any magnetic field, and we assume that the plasma to be collisionless for the time being. And so if we are assuming collisionless, and since we have applied no external electric and magnetic field, so what is there? E external is 0, B external is 0. And in such cases, you can remember that in our just last class we found that the Blasov equation may have the solution, not may, it must have the solution of the form Fs0 equal to Fs0v. So it will be function of velocities only. So we can go back and we can see that what we studied over here, the first case when E equal to 0, B equal to 0, then we found that the energy and momentum are conserved quantities. So the solution of the Blasov equation must be of the form, it is function of Vx, Vy and Vz. So we are using the same property over here, that because no external magnetic field or electric field is applied, so the solution of the Blasov equation will be of the form this Fs is equal to Fs0, that steady state value, and the fluctuating component S1. So this S1 is basically constituting the wave. It is the perturbation and it is assumed to be very small, and Fs0 is a space and time averaged value. The perturbation will create an electric field due to the charge imbalance caused by that effect, and that will be definitely governing by the Poisson's equation, divergence C equal to rho by epsilon, and rho is the charge imbalance, that is Ni minus Ne. That imbalance is caused by the electrostatic wave due to the varying electric field. Now we come here. So we have assumed that the plasma is collisionless for the time being, and we can write the Blasov equation in this form as we have already learned in our previous classes. So this Fs is the total distribution function, and it is Fs0, the ensemble average value, plus Fs1, the perturbation. And considering this, we can substitute this value of this Fs into this Blasov equation, and we can write it like this. You know that because this Fs0 is the time average value, so they will go out, and you write the equation in terms of the only the oscillating quantities, that is Fs1. So from the first term we are getting del Fs1 by del t, and this term is giving Vx and del Fs1 by del x. The last term is giving Qs by Ms. E is the electric field, then del Fs0 by del Vx, and then there is another term which is appearing over here. So what is that? There is Qs by Ms E into del Fs1 by del Vx. Now you know that E, the electric field, it is, we are assuming it is to be very small. It is a perturbation to the existing values. So this del Fh1 by del V, this Fh1 is also a so the small quantity. So when you multiply these two, then the whole quantity becomes a second order term, and we neglect this term because of that compared to the other term. So this one, so we neglect this term over here, and then we can write the equation in this form: del Fh1 by del T plus Vx del Fh1 by del X plus Qs by Ms E del Fh0 by del Vx. So this is equal to 0. Now we can look for a plane wave solution of the form Fh1 is equal to A exponential ikx minus omega t. This is the standard as we have applied in many of our problems in our school days. So the plane wave solution we are assuming of the form Fh1 is equal to A exponential ikx minus I omega t. Once we use this and put over here, the first term is giving you this minus I omega is coming over here, and you are getting back the Fh1. So the first term we are getting this one, and from the second one, because it is del x, so naturally you are getting ik out from this, and you are again getting back this Fh1. So that is one. That is what you have got, ik Vx Fh1. Then the last term is del Fh0 by del Vx. So this one we are keeping like this, and what we get finally, Fh1 equal to minus of I. You just change the side and then you can get it. So it is I into Qs. So this term basically, and Fh1 is coming out from these two terms, and that is giving you that minus I Qs by Ms omega minus kVx. So this one omega minus kVx, and minus sign is taken out. So E into del Fh0 by del Vx. So this is the expression for the perturbation which we arrive when we are exciting an electrostatic waves inside the plasma. Okay. Now, so what we have got actually for some species S, we are getting the perturbation as Fh1 equal to minus I Qs by Ms omega minus kVx E del Fh0 by del Vx. Now you know that plasma consists of these electrons and ions. So for ions, what you get, Fs1 equal to Fi1 equal to minus I Qi by Mi omega minus kVx and E del I0 by del Vx. So this one is for ions. Okay. And same thing, this is equally valid for the electrons also. So you just put E for S, and you get the expression Fe1 equal to I Qe by Me omega minus kVx. So this is coming over here, and then E del Fe0. So because the species is electron, so del Fe0 by del Vx. So now we know what is the density of these electrons and what is the density of the ions from these two. So this gives you the density of ions and this gives you the density of electrons. So the difference will create the charge imbalance, and that will create the charge density, additional charge density in that region. So and that charge density will create definitely an electric field. So divergence C equal to what you are getting, the E equal to e to the power ikx. If you say, then ik comes out and you get back E. So divergence is equal to ike, that is equal to rho by epsilon as per the Poisson's equation. And rho, what is that? This is Ni minus Ne, the charge number density, and when you multiply by the electronic charge, we are definitely assuming that is a only first ionized case. So Ni minus Ne, and when you multiply by the electronic charge, then that gives you the charge density. So that divided by epsilon completes the Poisson's equation. And for Ni, where we will reach, we will write just Fi1 minus Fe1, because Ni is nothing but Fi1 and Ne is nothing but Fe1. So when we write this equation in this form and we fetch the expressions for Fi1 and Fe1 into this equation, so just that what we have done here. So it is E by epsilon integration of dV is here, and then this is the ion contribution. So I have taken it from here directly here, and this is electron contribution I have taken directly from here to this place. Then what we are getting? We are getting see, there is electric field E, and here is also the electric field E. Okay. Now left side and right side both are having E in all the terms, so we cancelled E, and this Ik we have divided the right hand side. So Ik goes and E also goes, so we are left with only 1 on the left hand side, and on the right hand side we are putting Qi equal to Qe equal to E, because we know we are considering only the first energy case, and whether it is your electrons or it is the ions, if it is a first energy case, then we get Qe equal to Qi equal to E only. So E is the electronic charge. So if we put out that over here, and then we take K out from the denominator, then what we are left with, that it is coming as omega by K minus Vx, and K goes out over here, and from the left hand side we have taken one K on the right hand side, so that K and this K multiplies and gives you K square. And then the other thing what we are doing, actually we are now getting from this, actually you see that N0 we have taken here and we have divided here by N0. So this N0 goes, and E is over here, one E was here, so this was the electronic charge, and we have now assumed that Qi equal to Qe is equal to E. So this E and E multiplies and gives you E square. And N0 we have already explained, we have multiplied here and divided here, so that goes out, and this ME we have put over here because this ME is here, and then this term is now free from ME, but because we have taken ME common, so this ME in the first term it was not there, so ME goes up and MI is at the bottom, so ME by MI comes over here. So now what we are getting as the coefficient is N0 square by ME into epsilon. So you know that what is this value? Root over N square by M epsilon is nothing but the plasma oscillation frequency. So this one is basically giving you omega p, plasma oscillation frequency, or for electrons this plasma oscillation frequency for the electrons, actually N0 square by ME into epsilon. So the coefficient what we are getting is minus of omega square by K square. Now the other thing what we are having is dVx into this one. Now whatever is inside this red rectangle, we let us call it as GVx, because it should be function of Vx, because why? Because it is, this function is integrated over Vy and Vz. So whatever remaining will be there, that will be function of Vx only, because we have already integrated over Vy and Vz. So only Vx is, it will be function of Vx. That's why it is G of Vx, and this is ddVx, and what we have taken out is dVx, and dVy dVz we have already kept over here. So this is something your differentiation under integral sign. So we have followed all the rules corresponding to that, and we can write it as dVx, then ddVx GVx divided by omega k minus Vx, and left side it is 1. So and GVx we are defining it as ME by N0 MI, there is the coefficient, then integral over this function Fi0 and then dV by dVz, and then similarly there is a second term which is 1 by N0, and then integral of dvy dvz and f is 0. So finally what we are arriving over here, 1 plus omega e square by omega k square, and this u is nothing but Vx actually. We have just generalized it. So if it is Vx, then here is also Vx. So this is dVx d over Vx, you are differentiating, and this is function of Vx. So Gvx is what? This is the thing, as we have already told in our this thing previous slide. So this is the one. So this is Gvx and omega k minus Vx, and this is 1. So 1 equal to this one. So that is basically the dispersion relation for, this is the dispersion relation for the electrostatic waves in plasma. So right now we are just getting this expression, and we really do not know exactly how it looks. So to find that, we need to get into the nature of this GU and the kind of distribution function we are handling, that is Fi. What is the nature of that? Because Gvx will depend on the Fi, and what is the form of Fi. So depending on that, this dispersion relation will reach a final form. So what we do actually, the form of Gvx under Maxwellian distribution, that is for the plasma we are assuming the species are following Maxwellian distribution. So it is like this, that Fs0 is equal to n0 m by 2 pi kt to the power 3 by 2, then exponential of minus m b square by 2 kt. Okay. So this is the distribution function we are assuming. So we are assuming it is a Maxwellian, and this is actually, truly speaking, it is a very good approximation for many of the cases when you handle the plasma. Of course there are deviations, but this Maxwellian distribution works very well in a majority of the plasma which we apply in your industrial processes and laboratory plasmas. Now we are making some approximations over here. So we are using that half mv square of the order of half kt. So whenever we are getting this mvs square, we will be frequently replacing that with kt. So this is the thermal energy, and that is basically the translational motion caused by, and this is a half mv square. This is the translational energy, and we are equating with the thermal energy. So whenever there is a term mv square, we would like to replace that with kt wherever we require. Okay. Now you know that this is the form of our expression for this Maxwellian distribution, and we find here there is one kt is over here. Okay. So kt we are replacing with mvs square. So we put it over here, and this m cancels, and what you get, n0 by 2 pi to the power 3 by 2, and then this kt also we have replaced by vs. So vs to the power q, and then what we are getting over here is exponential minus vx square vy square plus vz square divided by twice vs square. So this is kt, and this kt is vs square m, and this m cancels. So we are getting this one. So whatever you are seeing here on the right hand side. So this is the form of the distribution function we would like to use for Gvx. So this is now the form. Now you know that what we have is that what is the form of Gvx? Let us go back here. So Gvx is basically this one, this one. So it is me by n0 mi into d by dy fi0 v plus 1 by n0 dvy dvz fe0 v. So here actually there is one iron electron term which is missing actually. So this is the electron term which also should be there. Okay. So apart from this one, that term is somehow it is not appearing over here. So it is not correct, and this one will be including this term as well, 1 by n0 into integral of dvy dvz f0 into v. F0 function of v. So this term is basically Gvx, and we are coming over here. So this is exactly the expression what we have written over here. So this dvy dvz, and what is the form of fi, fs0 you put s as I, then you get dy dvz n0 by 2 pi to the, and then vi cube. It was Vs cube, so S is I here, ion, so Vi cube. Then exponential, this Vx square, Vy square, Vz square are there, and then Vs square we replace S by I. So this is Vi square. So Vi is the thermal speed of the ions, and V is the thermal speed of the electrons. So same way, actually the electron part comes over here, dy dvz n0 by 2 pi to the power 3 by 2, then v cube, then exponential of this square of velocity sum, and then divided by twice of square of thermal velocity of electron. So this is exactly the expression which was there for Fe, and this is the expression which we have for Fi when we use this kind of conversion. So getting this, we can now integrate our Vy and Vz. What we will be left with? We will be left with Vx only. Okay. Now, when we do this integration of our Vy square and Vz square, then I have done this integration over here and dvy dvz, and you can just use this kind of formalism that Vy square plus Vz square, this should be Vz actually, is equal to C square. Then this polar coordinate, the integration is very easy. You can just write C dc into C d theta this much, and dc, that gives you the elementary area. And if you do this integration, it is very easy to find that it is 2 pi Vs square. Okay. So this give you this integration over Vy and Vz, that gives you 2 pi Vs square, and we will be using this for all the things, for electron terms as well as for ion terms. And if we do show, it is giving Vs square, so for electrons we will be putting V square, and for ions we will be putting Vi square. So when it is Vi square, and you see that at the bottom you have Vi cube, so Vi square and cube cancels, and you are left with only Vi in the denominator. Similarly, you get only Ve in the denominator for the electron terms. So finally, what you are getting, the expression for Gvx, that is Me by Mi, 1 by 2 pi to the power half, and then Vi, and then exponential of Vx square by twice Vi square plus 1 by 2 pi to the power half, and then Ve exponential of minus of Vx square by twice V square. So this is what you get the final expression for Gvx when you are using a Maxwellian kind of distribution. Now, so explicitly we have written here, so there are two terms, the left one is the ion term and the right one is the electron term. So now we would like to get what is the property of Gvx for Maxwellian distribution. So Gvx consists of an ion term and electron term. It is symmetric about your Vx because you can see the exponent is Vx square, and then since Vi is much less than V, at lower Vx only we will have this importance of this ion term, and it will not be important at the higher Vx values. So we will discuss on this in more detail in the next class, and so we stop here and we will begin from here in our next class. Okay, thank you.